Okay, guys, welcome back. We have finished chapter 4 last time, so now we get to start a new chapter. And as I hinted at last time, this new chapter will be all about chemical equilibrium, or basically reintroducing you to the ideas of equilibria that you have already learned, and also applying these rules of thermodynamics, which we've talked about, to this idea of equilibrium. So what is equilibrium? You can define equilibrium in many different ways. There's the philosophical understanding of equilibrium, which is what Stefane Lupasco is talking about up here. Okay, this is the philosophical understanding of equilibrium, or not changing. Okay, and he's stating that equilibrium, or the process of no change happening, no net change happening, is the state of death. So once you die, or not you in particular, but death in general, when death occurs, no change exists, and therefore you are at equilibrium. Okay, so there's many different ways of thinking of equilibrium, but in this particular chapter, we are going to deal with an idea of chemical equilibrium. Okay, chemical equilibrium. Now, chemical equilibrium is the point within a chemical reaction where no net change occurs. Okay, so it's the point in the chemical reaction where no new net change is occurring, and we are going to use thermochemistry, or thermodynamics, to describe it. So this is what we've been building up to this whole time. My smiley face man is a little bit creepy. Whoa, I don't know. That might be even more creepy, but it is what it is, okay? So we want to use thermodynamics to describe chemical equilibria. Or we want to see if we can use the thermodynamics that we've developed in order to describe equilibria in a little bit more detail, okay? So let's look for an example, okay? If we have a bucket of water, okay, so we have H2O in the bucket, and into this bucket we throw a cube of sodium metal. The question that all chemists ask, basically in every chemical situation, is this system at equilibrium? Okay, is this system at equilibrium? The answer is an emphatic no, of course. You know what happens when you throw sodium into water. We expect some sort of violent reaction to occur. Okay, we expect some sort of violent reaction due to the chemical reactivities involved between water and sodium. The exact chemical reaction that we expect looks something like this. If we react 2 sodium with 2 water molecules, we end up with, oops, bad arrow. We end up with 2 aqueous sodium atoms, 2 hydroxide ions, and 1 mole of hydrogen gas. Which, by the way, if you didn't know, when you throw sodium into water, it explodes. And the reason it's thought to explode, although this is debated in the literature, which is rather interesting, is that this is an extremely exothermic reaction. Okay, so delta H is very small, or very negative, and because of this, it puts out an inordinate amount of heat. Okay, so it heats up the surroundings, and it also releases hydrogen gas into the surroundings. Now, when you have heat mixed with hydrogen gas that already has oxygen gas around it, because it's in ambient conditions, you end up with big fire. And that's what happens. It explodes. When you throw this into water, you get a nice little explosion. I would show you in the lab, because this is a really fun demo to show people. It's quite It's quite awesome. It's like a little firecracker. However, due to the plague, we are unable to do so. Maybe next semester, if you guys want to see it. I don't know. Some of you have probably seen it already, but if you want to, this is always a fun reaction. So let me know. If you want to see it, we'll do it. Okay, so is this at equilibrium? No. It's going to proceed by this reaction here, and it's going to proceed to completion. Okay. However, once this reaction is complete, there are no new net changes. So at that point, the system is at chemical equilibrium. Okay, but at the very beginning, when you first add sodium into the water, it is not at chemical equilibrium. There has to be some sort of equalizing of the forces or the chemicals involved. Okay, and we'll get back to that in just a second. Let's consider a different system. How about an insoluble salt? Oops. And of course, you guys know that insoluble should have quotations around it because you know that everything is somewhat soluble. However, very minute quantities of something could be soluble, so it seems like nothing is dissolving. If you were to take, for example, the same bucket of water, and you were to put in some lead chloride crystals. Okay, lead chloride is has a very, very low solubility constant, and so very little of that solid will form aqueous ions. Okay, however, even though that's true, we have two chemical reactions that are happening at the same time within this reaction vessel. We have lead chloride, the solid lead chloride, dissociating into lead 2 plus, aqueous ion, and chloride minus, 2 chloride minus, aqueous ions. Okay. Now we also have the back reaction occurring. So we have 2 chloride ions attaching to one lead 2 plus to form lead chloride solid. Okay. Both of these reactions are occurring simultaneously. Both are occurring simultaneously and with a rate that is equal. And when the rate is equal, it's at equilibrium. Okay, so when the forward and backwards rates are equal, that means that you're creating ions just as fast as the ions are reacting together to form the solid. So there's no net change, so you're at equilibrium. However, this is said to be a dynamic equilibrium, simply because it's not that nothing is moving. You actually have these reactions still occurring, but there's no net change. There's no change in the concentration, and at this point it's said to be at dynamic equilibrium. Okay, so there's a constant breaking and reforming of lead chloride. So this is indeed at chemical equilibrium. So the next question after we defined equilibrium should always be why. Why in the world does a system come to equilibrium? Let's see if we can suss this out. Okay, let's look at an example where we have some sort of rock on the side of a mountain here. Okay, in this case, let's call this case 1. Obviously, the rock is not at equilibrium. As a matter of fact, the rock will have a huge propensity to fall down the mountain. Okay, so this is not at equilibrium. However, if we look at a different case, say maybe after the rock has fallen down and the rock is at the very center of a trough, we can say that this definitively, the rock will not move any longer, And so this is said to be at static equilibrium. Okay, no motion is happening, and yet this system is at equilibrium, and therefore it's said to be static. Okay, so that's opposed to dynamic, where the reaction or some sort of process is still occurring, but it has an equal and opposite effect. Okay, so in this case, why does the rock fall? Why does the rock fall? Well, the rock has excess. The rock has excess gravitational potential energy. Okay, the reason it falls is because it has excess gravitational potential energy, and there's no force counteracting that excess gravitational potential energy, so it falls. The potential energy is transferred into kinetic energy, and the rock falls. Okay, it goes towards the center of the Earth. Now, in this case, the rocks. So the rock still has gravitational potential energy, but gravitational potential energy, I'll just write it like that, grape. The rock still has kinetic or potential energy. However, in this case, the rock is being, or the force that's pushing down on the rock is being counteracted by the force that the Earth is exerting on the rock. So there's two opposite and equal forces that are acting on this rock, and therefore, due to Newton's first law of motion, right? Due to Newton's first law, since these two forces are acting on the rock and they're balanced, meaning that they're equal but they're in opposite directions, the rock doesn't move. It's at static equilibrium. Okay, so there is this interplay between the equalizing of forces. Okay, so once these forces are equalized, once these forces are equalized, it comes to an equilibrium. Okay, so this is beginning to answer the question of why, at least from this simple gravitational perspective. Okay, but what we want to see is an analog to chemistry. Okay, an analog to chemistry. It's nice to think about simplistic pictures like this, but at the same time, we are more interested in chemistry. So the question is, can we make this metaphor, or can we make this example analogous to chemistry? And the answer is yes. The same principle can be applied to chemistry, whereas instead of gravitational forces counteracting each other, in this case we have chemical forces. Okay, so chemical forces are balanced at equilibria, or at equilibrium. Okay, what are these equilibrium forces? Or what are these equalized forces? Well, we learned about one in the last chapter. Chemical potential. Okay, chemical potential. And it is exactly analogous to gravitational potential. Okay, it is some potential for this substance to carry out some sort of chemical process. And if you remember the way that we defined it, mu is equal to the change in G with respect to the change in the number of moles of some ith substance, with temperature, pressure, and other molar quantities are constant. Okay. Since the G varies, or the total G for the system varies with each n sub I value. Okay, so it varies with each one independently. So the total G of the entire system must change. Okay, so the total G of the entire system must change with some sort of chemical reaction. And we want to be able to track this change, or we want to be able to track how G varies with the progress of the reaction. Okay, so we need to define a new quantity here, and this is called extent. And it's symbolized with this freaky Greek Z letter. Okay, freaky Greek Z. That's what I like to call it. And it simply is the progress, or it represents the progress of the reaction. Okay. So if we define n, some value n at time t equals 0 as n naught, then we can define crazy E letter to be equal to n sub I minus n sub I 0 divided by V sub I. Okay, where this n naught is this guy here. N sub I, whoop, bad. N sub I is the number of moles of the ith component at some time t. Okay, and V sub I is the stoichiometric coefficient. Okay, of that ith substance. Now for reactants, it is negative, and it is positive for products. Okay. We can define, furthermore, based on this, if you look at it from a perspective of reactants versus products, we can make a few definitions. Ooh, that was a really good one, guys. Look at that. Look at that. Beautiful. Weird squirrely E thing. Man, that's almost like a script. I wonder if I can copy that. Can I copy that? Trying to figure out how to use my... let's see here. I want to see if I can copy this. Sorry, this is a bit of a foray. Ooh, lasso select. Oh yes. Guys, we have it. Can I make another one? Oh my goodness gracious. Look at that. Oh wait, I can just move that one. Okay, what if I come over here and paste? Oh my gosh. This is amazing. I love technology. Okay. Sorry. Yeah, look at that. Really beautiful E squiggly thing. We can furthermore say about E's value. Oops, uh-oh. No, I'm stuck in lasso. We can say something about E's, or the extent's value at any particular t. Okay. The extent's value at any particular t, it turns out, is the same no matter what substance you use to calculate. Okay. So yeah, you can use any of the substance within the chemical reaction, and no matter which substance you use, it turns out that it will always have the same value. Now, if you want to verify this for yourself, there is an example in the chapter, which is example 5.2. Okay, so they go through and they calculate the extent for a bunch of different reactants and products, and it doesn't matter which one you use. At any particular time t, you will have the same extent of the reaction. Okay, and because of this, it is a consistent way to follow the reaction progress. consistent way to follow reaction progress. So if this guy is positive, okay, then the reaction moves to the right. Basically, it moves towards the products. If this guy is negative, then the reaction moves to the left. Okay, pretty cool. So we can know a lot about the reaction depending or based on the value of this extent property. Okay, so I want to get back to this idea of the change in G with respect to the change in the molar quantity. Okay, so if we look at the infinitesimal change in n, or n sub I, is given by dn sub I is equal to v sub I, which is that stoichiometric coefficient, multiplied by d times squiggly. Okay, so the infinitesimal change in the extent multiplied by the stoichiometric factor is equal to the infinitesimal change in I. Now notice I'm not putting an I subscript here, and that's because epsilon, or not epsilon, I think this is zeta actually, the lowercase zeta. This value is constant over all of the different substances, so it doesn't have a subscript, which will become important later. Okay, so as n changes, so does G. Recall, right? So dG is given by negative S dt plus V dP plus the sum over all species of the ith species chemical potential multiplied by the infinitesimal change in n. Okay. Now we can set constant T and P. Okay. At constant T and P, this is why dG or delta G is so useful. Okay, is because constant T and P is a very easy thing to achieve in the lab, and as a matter of fact, usually most things are at constant temperature and pressure. Okay, so if we set constant temperature and pressure, then this becomes dG, and then becomes the sum of chemical potentials times the infinitesimal change in I. Okay, now I'm going to substitute in for here the infinitesimal change in n from above. Okay, going to substitute it in right there, and I from this will get equal to the sum of the ith component chemical potential multiplied by the ith component stoichiometric value multiplied by d, or the infinitesimal change in the extent of the reaction. Now, since the infinitesimal change for the extent of the reaction is constant, or it doesn't change for any of the ith values that this is summing over, I can divide both sides of the equation by this value, and therefore end up with the partial of G with respect to the partial of the extent at constant T and P is equal to the sum over I space of mu I VI. Okay. Now, recall from chapter 4, okay? Recall from chapter 4 that we defined this value at equilibrium. Delta G, or dG, is equal to 0. Okay? Now we're going to define at chemical equilibria, or equilibrium. We're going to say that delta G reaction is equal to 0. Okay? And when this is basically being defined as this value up here. Okay, so we're saying that delta G reaction is defined as the partial of G with respect to crazy Z thing of TP is equal to the sum over I space of the chemical potential of ith component multiplied by the stoichiometric factor of that ith component. So at equilibrium, all of this is equal to 0. What is this actually saying? What does this mean? Well, what this component is saying, if the change in G with respect to the change in Z at TP is 0, if we just look at a graph of G versus reaction extent, okay, there's going to be some function that this takes. And this value, the change in G with respect to the change in Z, is only 0 at the minima. Okay, so at minima, this value dG over the d extent Tp is equal to 0. Okay, so this is the equilibrium point for this reaction. Okay, and it's going to be reached within the reaction because it's at a minimum. Okay, so this is very similar, or starting to look very similar to the rock on the hill concept, right? G is just a form of energy, an expression of energy, and all we're saying here is that we're minimizing the energy of the system, just like we would for a rock on the side of a mountain. Okay, so it's very analogous to that original example. But the question then becomes, how does this actually look for a molecule? Okay, well, how does this actually look at the molecular level? So if we have some reaction happening between two species, we'll say A and B, and we have their specific G of the species. Okay, so each of these species is going to have some Gibbs energy. Okay, and as the reaction progresses, this should decrease, something like that. Okay, so there's no minima here. As a matter of fact, it looks to be like this. This situation looks to be that the reaction would just flow all the way to B. However, there's something else that's involved here, and this is known as the Gibbs free energy of mixing. Okay, so there's some decrease in the energy that occurs when you mix two things together. Okay, and the best or the minimized is usually about 50-50. Sometimes it's different. Okay, so this can move all over the place, the actual minima of this G of mixing. Now, the total process is an amalgamation of these two, and what you end up with is, instead of something like the first plot, which is just a straight line, you end up with something of a curved line, like this. So this is both the process, the chemical reaction that's occurring between A and B. So this is, I guess we should write this out. So this is total G, okay, for the overall reaction. And you can see that this now has a minima here, and this represents equilibrium between the two, okay? So let's look at a generalized gas phase reaction. Our favorite gas phase reaction, which is just A moles of A decomposing into B moles of B. Nice and simple. Okay, we can define the delta G of this reaction as equal to the sum of mu I times Vi over all of the I's, all of the substances. Okay, so in this case it equals mu B times B minus or plus mu A times negative A. Remember, the V value always takes on the negative if it's a reactant and positive if it's a product. Okay, so we can say that delta G reaction for this case is equal to mu B. Actually, I want to write this a little different. B times mu B minus A times mu A. Okay. Now, recall we already have an expression for mu. Mu is equal to mu naught plus RT times the natural log of P over P naught. Okay. Now I'm going to substitute in this expression for each of these, and we can now write delta G reaction as equal to B times the first mu, which is MB, so this would be M naught B plus RT times the natural log of PB over P naught. Okay, minus A times mu naught A plus RT times the natural log of PA over P naught. Okay, using the identity of logarithms and a little bit of algebra, I can rewrite this as B times mu naught B minus A times mu naught A plus RT times the natural log of PB over P naught raised to the B divided by PA over P naught raised to the A. Okay. Now, furthermore, we can find this, or we can realize this is actually just delta G reaction naught. Okay, where delta G reaction naught is equal to, in a generalized form, of the sum over I space of mu I naught times VI. Okay, so you can see that that's true here. And furthermore, we're going to define this, all of this stuff in here, okay, as Q, the reaction quotient. Okay, the reaction quotient. This is the same reaction quotient that you guys learned about in Gen Chem. Same one, same reaction quotient, exact same reaction quotient. Okay, and we'll see in a little bit how it transforms into something even more useful. Okay, therefore we can write this whole bit as delta G reaction is equal to delta G standard reaction plus RT ln of Q. Is this starting to look familiar to you guys? It really should. Okay, and we've derived this from first principles. Now, in general, we can write delta G reaction as the sum of the delta G formation standard for the products minus the sum of the delta G formation standards for the reactants. Okay, so we have a generalized way of writing delta G naught, and we can write a generalized way for Q as well that works for any reaction. If we have the product over I, products, of P sub I over P sub naught raised to the absolute value of V sub I divided by the products over J products, J reactants of P sub J divided by P sub naught raised to the V sub J absolute value. Okay, so these are generalized ways that you can find delta G standardized reaction and Q for basically any reaction. It doesn't have to be our favorite generalized gas phase stuff. Okay. Now, delta G formation are tabulated. Okay, just like delta H formation standards are tabulated. So we can look these up, and we can use these guys to get delta G standard reaction for any reaction that we care about. Okay. A word of note, however. Okay, so delta G reaction. What's the difference between delta G reaction and delta G reaction not, or standard? So delta G reaction can change depending on the conditions of the system. Okay, so it depends on conditions. Okay, delta G standard reaction is the change in G for reactants and products in their standard state. So in this case, it is a characteristic value of a reaction. Okay, I don't want to go so far as to say it's a constant, because it's not, but it is a characteristic value of a reaction. Okay, so if you're looking at two different reactions, or the same reaction under two different conditions, delta G standard reaction will likely be the same. Okay, and I'm also going to define two new terms here. If we have delta G less than 0, this is called exergonic. Okay, and if you have delta G greater than 0 for some process, this is called endergonic. Okay, and these are synonymous with exothermic and endothermic. Okay, just to throw out those terms. Okay, so at chemical equilibrium. At chemical equilibrium, we have delta G reaction is equal to 0, right? So that means that 0 is equal to delta G reaction not plus RT natural log of Q. Okay? That means that we can rewrite this as delta G reaction not is equal to negative RT natural log of Q. Now, this delta G is characteristic of the reaction. Okay, so it doesn't change. That means that Q must necessarily, therefore, be characteristic of the reaction. And at equilibrium, indeed, that is the case. This is a characteristic of the reaction. And it's called K, which is the equilibrium constant. Okay, so we've gotten to K, equilibrium constant, which you guys, I know, are familiar with from Gen Chem and from analytical chemistry. So we can further write this as delta G reaction naught is equal to negative RT ln of K. And this is a pretty famous form, but you may be more aware of this in the exponential form, which we can take by dividing both sides by negative RT. So we end up with negative delta G naught reaction divided by RT is equal to the natural log of K. And if we raise both sides to the exponential factor, we find that K is equal to E raised to the negative delta G naught reaction divided by RT. Okay, these are the two forms of this equation. They're both fairly famous, and they relate delta G standard reaction with the equilibrium constant. Okay, so if you know one, you can find the other. Very useful, very important. And we got there completely from first principles. As a matter of fact, these equations were first derived from first principles. So the only reason that you know that equation, you know that it happens, is because somebody took the time to actually derive it for derive the expression between delta G standardized reaction and the equilibrium constant K. Okay, I'm going to leave it off there for today. We've gone through a lot of material, and we will pick it up there on Monday of next week. I hope you guys have an amazing Friday and an amazing weekend. Don't forget, I will be posting Chapter 5 homework very soon. That'll probably be due in about a week or so. And then I also posted a lab report. So you'll be writing a paper or a research paper on a famous experiment. And this time we'll be doing the Joule-Thomson experiment. Okay, so you write, I think it's 5 to 8 page paper describing the experiment and all of the derivations that go into that. And then in a couple weeks we'll do another one of a different famous experiment, in which case you guys will do the same thing. Okay, and that's how we're going to keep our lab grade going. I know some of you expressed concern about your grades, and not having the lab grade would certainly hurt some of your grades. So we're going to throw that in. Okay, yeah, but the due date and everything is on Canvas. Other than that, if you have any questions, feel free to email me or chat me on Google Hangouts or whatever. All right, take care, guys.